Good afternoon, class. Today we're going to study acids and bases. We're going to learn what they are. We have 4 objectives that we're going to reach today. The first objective is that we're going to understand the concepts of pH, acidity, and basicity. Then I'd like somebody to read the second one.
Understand the logarithmic nature of pH and the relationship between hydrogen ion concentration and pH.
Yes. And know normal pH of blood and interstitial fluid, and understand the role of buffers. Those are the ones we're going to learn today. To get us started, I have a KWL chart. I want you to take a couple of minutes to let us know what you already know. Just the K portion, what you know. And the items that we want to know what you already are aware of. You can't use the textbook, or pH, the pH scale, the logarithm, acid, base, neutral, and buffer. All right, so take about a minute for each one and just scribble very quickly what you know about these topics. Okay, we have 7 minutes that have passed. So I'd like for somebody to volunteer to share with me what you already know about pH.
It's the concentration of hydrogen.
Concentration of hydrogen, okay. Anybody else?
It's on the scale from 0 to 14.
That would be the scale, the next thing, right? Okay, so we notice what it is numerically on a scale from 0 to 14, so we've already handled the pH scale. All right, so this is rudimentary, just the basics. Then a logarithm. You don't have to know, we'll learn it as we go today. Acid.
It's 0 to 5 or 0 to 6.
Okay. Base.
8 to 14.
Okay, and what is a buffer?
Found on the blood plasma.
A buffer is found on the blood plasma. All right, so you have some working knowledge of these concepts. By the time we finish today, we will understand them in much more detail. So what a pH really is it measures the amount of hydrogen ions in a solution. So what is a solution?
Combination of 2, solute and solvent.
A solute and a solvent. So anytime we have a solution that has a solute and a solvent, we can measure the potential of that hydrogen ion. In some cases, the hydrogen is released, and other times they are received. So when we look at the potential of hydrogen on the pH scale, how many hydrogen ions do we have? So when we're looking at hydrogen ions, what's an ion before we go further? An electrically charged particle. So when we look at ions, we're looking at sodium, we're looking at chlorine, we're looking at potassium, those types of things. And then we need to know that when we have within our bodies, we have certain solutions that need to remain stable at a particular pH. So when we look at pH, we're going to look here. And I need somebody to come forward and write the number on this scale where you would have your acid, and write the number of the lowest acid that we can have.
So we write it.
So somebody go right on that red line.
The lowest.
That's going, yeah, the lowest number for an acid. 0. Excellent. Excellent. Now I need somebody, thank you, Tyler. I need somebody else to write the highest number for a base. Does anybody know the other word for a base?
Alkaline.
Alkaline. So put a slash and write the word alkaline, please. And that will end a lot of confusion in the future. And we have somewhere that we call neutral. How about you, Maribel? Showing us where neutral is and explaining to us what you already know about neutral.
Neutral is between the acid and the base. It's just a number that separates. It's like in the middle. And the middle number that is between the acid, because we count from 0 to 14, the middle number is 17. And I think water is neutral, so it's just not too acidic, it's not too basic, it's just medium.
Okay, all right. It's like a neutralization reaction. So when we look at neutral, N-E-U, that's okay. When we look at neutral, then we know that what item is neutral? What solution is what?
Water.
Water. Is it just any kind of water or is it pure water? Pure water is neutral, okay? So give me an example of something that would be acidic, that's in the body. Stomach acid, which is hydrochloric acid, HCl. So we're gonna go 1, 2, 3, 4, 5, 6. Get the neutral, 8, 9, 10, 11, 12, 13, and then we're 14. We have the whole scale. So what is the pH of this hydrochloric acid in the stomach? What's the range? 2 to 3? Sometimes we see 1.5 to 3.5. Sometimes we see 2.5 to 3.5. So we're going to put both of those numbers on there for hydrochloric acid. And give me an example of an acid that we have in just everyday use. Think about when you're driving your car. Battery acid. Is battery acid harmful to human tissue? It can be. Acids are harmful. They can burn you, and they can cause damage to your tissue, yours, a plant, or any living tissue, yes. So, and a base that we use for cleaning would be, pardon? Ammonia and bleach. And did somebody say something else?
She said Clorox.
Yeah, Clorox is a bleach brand, yeah. So just like we have those products that we use for our purposes, there are acids and bases in our bodies that make sure that all of our biochemical reactions are taking place normally, okay? So we have the hydrochloric acid over here, and we have a neutral. We know that's pure water. Why? What's the difference between pure water and water from a sink or bottled water? What's happened to make it pure water that is neutral? It has all those other chemicals and sediments removed. Very good, Tyler. All right, so as we move on, we know that pH is the potential of hydrogen, right? So as we look at the potential of hydrogen, and we look at the first objective item, pH, we know that, right? Potential of hydrogen. So if we're looking at the potential of hydrogen, and we know that if we look And the next thing is going to be logarithmically, and it's written logarithmically as negative log, or it'd be -5 pH, all right? Or log -6 for the pH, right? All right? Either way, ask your question.
What is the log?
Speak up, please.
What's the log?
Log is logarithm.
Mhm.
And that's our second objective because we need to understand the logarithmic nature of pH and the relationship between the hydrogen ions and pH, right?
Okay.
So that's a good question. What is the logarithm? Logarithm is mathematical and it has a base of 10. It's a base 10. So 1 times 10 to the -5th is what this would be, right? So when we're looking logarithmically at the pH, so a -5 would have a pH of 5. Because when we bring it out of that bracket, the negative makes it a pH of 5. So the -6 would be a pH of what? Okay. All right. So we know, and you've already shown that you understand the acid, the base, and the neutral. Now, so we can check off that objective, we met it. We understand it now. So logarithm, we know that there's a logarithmic nature of pH, and we just showed that a -5 or a -6. So let me ask you this. If we were looking here, and we looked at the pH of 4 and the pH of 6, and we had negative log, and then we had the -6 and log of a -4, we see that, so because now we have to show the relationship between that logarithm and the pH, right?
Right.
So we know that this has to do with pH. So how many places on the pH scale are the 4 and the 6? 2 places. So if the 4 and 6 are 2 places on the pH scale, then if one place logarithmic is 10 to the first, 2 would be 10 to the what? Second power. And 10 to the first power is what value? Mathematically 10, and 10 to the second is what?
100.
Because we multiply, right?
Yeah.
So, what does that mean as far as pH is concerned?
It's 100.
Okay, which one is 100 times more acidic?
4. Yeah.
Which one?
4.
Okay,
The 4 is.
so we're agreeing now
Yeah.
that the 4 is 100 times more acidic than a solution that has a pH of 6.
Yeah.
Excellent, excellent, excellent. We got our thoughts together, now we have it. So that's how we show that we understand the relationship between the logarithmic nature of pH and the relationship between hydrogen ion concentration. I think that activity showed us that. Now, we know that the hydrochloric acid that we find in our stomach is somewhere between 1.5 and 2 and 3.5, and pH in each person's body varies because we know we're different biochemically, right? Some people's pHs tend to run a little high, some a little lower, but whatever your individual pH is probably based on what? Your body mass, what you eat, and what else? Heredity, your genetics. You inherit it from your parents and they inherit it from their grandparents and on and on. So all of that's related. If you eat more of a certain type of food, you might have a more acidic pH. If you eat others, you might have a more basic or alkaline type of pH. So today, as we're going through these objectives, we have 2 labs that we're going to complete. One of them have to do with buffers. So we're going to move on to the next objective, and we need to know the pH of blood. What is the pH of blood in your body? What's that range? Anybody know?
7.35 to 7.45.
Okay, 7.35 to 7.45 is equal to the pH of blood. All right. I normally like to write that in red because it reminds us of blood. All right, so that's the range of blood within the human body, pH. So what happens if we have a pH of 6 for our blood? Or pH of 9 in our blood? What's going to happen? What do you think?
Hydrogen.
Denaturing, she said. What'd you say?
I said more hydrogens or less hydrogens.
Yeah, but how's it going to affect us? If we have denaturization of the blood in our bodies, how is it going to affect us? If we have the pH too low or too high, then we're going to have a disease process, right? If it gets too low or too high, then our life is going to cease. We're going to have, if it doesn't get to the extremes, then we will have activities occurring in our bodies where there is an illness that's taking place. So the doctors will have to try to do something, doctors, nurses, healthcare professionals that you're going to become will have to figure out what's the problem, make a diagnosis, and figure a way to rechannel that pH back into the norm, okay? So, in the beginning, you said that the pH of an acid is 0 to 6, right? To correct you, the pH of an acid, and let's see acidic, is 0 to 6.99. All the way up to 6.99 is acidic. It's going backwards, right? We know neutral is right here. And then when we go 7.1 to 14, that's your basic or alkaline, right? So because a lot of people think you stop at a 6 for the acid and you start at the 8 for the base, we need to correct that. It goes all the way up to where right before the 7 for the neutral and right after the neutral where the slight basic or alkaline starts. All right, very good. So we truly understand acidity and basicity right now and what the pH is. We understand logarithm. Now we need to know we know the pH of blood. What is the pH of intracellular fluid?
It's neutral.
Intracellular fluid, I'm going to just start writing that word.
Intracellular fluid is normally it's neutral.
It's neutral, so if it's neutral, what would it be?
7.
So 7.0. So you notice from this that if the intracellular fluid is neutral and the blood is 7.35 to 7.45, then different solutions in our body have varying pHs, right? So we know now the pH of blood and interstitial fluid. So that's how we can distinguish lymph or other interstitial fluids pHs if they're within normal boundaries, or if the blood's pH is within normal boundaries. Because we want to keep them 7.35 to 7.45 for the blood, right? And we want to keep the interstitial tissue as close to neutral, 7 as possible, because it's mostly water. Although the blood has water, it has a whole lot of other solutes that's done what in it? We have a lot of other solutions that are dissolved within the blood, right? That's why when we do a blood test for the medical providers, we can tell what your norms were, if your blood sugars are normal. And the blood sugar word is what? What's the word for blood sugar? Glucose, excellent. We know that if your albumin, and those are some of the things that are going to be in the lab today. We're going to test albumin levels. We're going to test sodium and chloride levels, just like regular medical tests do. And if we're going to test pH, do you know what instrument we're going to use?
Strips?
pH strips. Has anybody seen the pH strips?
Yes.
They look like this. I know you've seen them. And there's an indicator on the bottle, so based on what color we find when we dip the paper into the solution, we will determine what the pH of that solution is, okay? I'm gonna leave it right there for now. One other thing before we get into the lab to show how these work, the pH, the acids, the base, the interstitial fluids, as well as the blood and albumin, which is a protein, how they're going to function in the blood, and see how we can keep them stable. What's that term we use for stabilizing our bodies? Homeostasis. And what part of our body do we try to keep stable? Is it external or internal? Internal. So it's the blood. We need to keep that 7.35 to 7.45 because we go down to 6, it's a problem. We go up to 9, it's a problem, right?
Yeah.
So we understand now interstitial and blood pH. So now we need to understand the role of a buffer. Who knows or has an idea of what a buffer does?
It helps to lower the chances of changes in the pH.
Say that again, but louder.
It helps to lower the chance of change in pH.
It does. It reduces the chance that the pH is going to change. It tries to stabilize the pH in the body so that everything is working homeostatically. So that's the role of a buffer. So I have a question for you. If we have a buffer, and one buffer we use 100 milliliters, and the other one we use 50 milliliters, right? All right? And then the change we notice with the 100 milliliters of hydrochloric acid, let's specify what we're dealing with. So if we use 100 milliliters and we get a change of 1.6 here, and then we use 50 milliliters here, and we get a change of 1.65, which is the better buffer? Oh, this is A, and this is B. So if with A we use 100 milliliters, and the change that we received was 1.6, and with 50 milliliters is what we used, and we got a change of 1.65, which is the better buffer, A or B? Why B?
Because it has more of a buffer.
Buffer means you're not going to change, right?
Yeah. Oh.
Oh, what O?
Because there's less change in A. Yeah.
Because there's less change in A, and what else? We use more of a solution of hydrochloric acid, and we have less of a change. Actually, we use how much more? We use twice as much hydrochloric acid in A, and we receive a lesser change than we did in B using half that amount. That's what a buffer does. You can use double the amount, triple, quadruple the amount, and the change is less. You stay stable. That homeostatic is the same. Does that make sense?
Yeah.
All right, so now I'd like for you to open your books, your lab manuals, to page 197. Exercise review, and we're going to use this as an exit ticket to see how much you have understood. And the first one asks, a solution has a hydrogen ion concentration of 1 times 10 to the negative 5th. Let's write this because we want everybody to see what's happening. We got 1 times 10 to the negative 5th. That's the solution. What's the question, Mirabelle?
What is the pH?
What is the pH for 1 times 10 to the negative 5th? What's the pH, Bridget?
5.
The pH is 5. So that confirms that you understand the relationship between logarithm and pH. The next question, 100 drops of hydrochloric acid. Oh, I think I just did that one for you. Because you use 100 drops of hydrochloric acid in A, you got 1.6 units of change, and then 50 drops to B, and you got 1.65. That's what we just did. But can you explain it again so that you're never confused again?
A is a better buffer because there's used twice the amount of solution and got less change.
Okay, very good. What's the third one? What might limit a buffer's ability to prevent pH change? Is there anything that can cause a buffer not to function as properly? It's concentration. It might be denatured. Excellent. All right. So now that we understand these concepts, pH, acidity, basicity, pH scale, the logarithmic nature of pH, and how it relates to the hydrogen ion concentration, and we know the normal pH of some solutions in our bodies and how buffers work to try to stabilize them, right? Now we're going to move on to our laboratory activity. It's quite extensive. We have lots of materials here, and we're going to show how buffers, first of all, maintain homeostasis within interstitial and bodily fluids, interstitial fluids, blood, and other types of fluids. We're also going to learn, after we learn about how buffer works, then we're going to look at respiratory compensation, how the body tries to compensate when we have a buffer that's not functioning properly, and to try to bring it back within norms. That's what today's entire lab is about. All right, so if you would, look here in the lab manual. We're gonna look on page 193, and it explains to us that when we have a buffer, like we had HA and A, these are the buffers, HA and A, and it's a reversible type of solution. We have H plus A, right? If we move in the right direction, and when we go back left, we have a combination. So these solutions are called, oh, A is negative, yes. All right, so, one minute. So we're going to show in our lab activities how this occurs using hydrochloric acid, bicarbonate, albumin, sodium chloride, and a few other items. First, we're going to start with the test strips, and Are there any questions that we have regarding what we've learned today prior to going into the lab?
Before we move on, you were saying that the hydrochloric